Okay, in this video, we'll go over forces and torque and multiple objects. But we're going to start with something also, another topic right here, which I'm not going to give away yet. So here we have the same picture, the rod that's supported, free to rotate around point P. One end of the rod is held up by a thread. Here we have mass and length of the rod. And question A is, what is the angular acceleration uh, when the thread is cut? And my alpha looks worse and worse. There we go. Something like that. Okay, we'll start with a free body diagram. And I saw that I actually took time to make the rod, so I guess I'll do that here. Make the rod look nice. And for our free body diagram, again, we have gravitational force acting at the center of mass. And we do have a force holding it up. We'll call it force P, holding up that rod there. When we cut the string, cut that. These are the only forces that would be on it. Now, before we cut the string, depending on where I put that thread, okay, there would be a force from the thread, maybe Ft, we can call it. Wherever I put the thread, that's where the force would be. But I'm going to say we've just cut it. I'll get rid of that. So when we just cut it, it will look like this. Okay. Now it's rotating around point P, and so forces causing torque is really just the gravitational force. We've done this before. And you can call this, since there's only one, I'm just going to call it R. So let's figure out part A. What is alpha when the thread is cut? The sum of torque is I alpha, which is R times mg. Rotational inertia for a rod is ml squared over 3. Guys, I've been doing that wrong this test sheet. Okay, no, that one has 3 in there. Okay, that one has 2, but it's supposed to have 2. Sorry, I just had a panic moment there. All right, times alpha. And okay, for today, it's important. We're gonna keep I intact here. So you can cancel M, right? But don't do that. No, I wouldn't do that. Leave M because we want to make sure we want to know while solving this problem what is I equal to. You'll see why. You'll see why. So what is R? It's half of L, so that's 0.75 times the mass, which is 6 times G equals 6 times 1.5 squared over 3 times alpha. 0.75 times 6 times 10. 45 is, cool, which is 10 radians per second squared is alpha. Okay. Now I've realized I've run out of space, but we're going to try to squeeze this in here. Part B says, what is omega, or what is the angular speed when the rod is vertical? And luckily, I kept this from earlier. Now, I need space here, so maybe I'll leave it right there. So the rod is initially horizontal here, and then we cut the thread and it's going to move down here until it's at a vertical position there. I mean, it'll keep moving, it'll kind of oscillate back and forth here, but anyway, that's what it looks like. We want to know what is omega when that rod is vertical. And you can pause the video, think about what you would do How would you calculate omega? And you might be thinking to use kinematics, right? Because we have equations that relate all of these quantities together. But the problem is that these and the corresponding equations only work when alpha is constant. And alpha is not constant here, and I'll show you why. When the rod is horizontal, it has mg pointing here. It has distance r, and those are at 90 degrees, so it's perpendicular. And so the torque is equal to r times mg. When the rod is about so far, mg is still pointing down, but here's r. Well, r is not perpendicular with all of mg, it's only perpendicular with a component of mg. And the component is going to be less than mg, so torque has gone down. And if you look at this equation, yeah, if torque changes, I is not going to change. If torque changes, then alpha changes. And so alpha cannot be constant. And of course, down here, we'll just show it. Um, there is no torque at that point. So kinematics doesn't work. But what does work, I'm going to need this picture again. So what does work is the concept of energy. Okay? The way I like to think of it is, this is just me personally. Sometimes when I think of an object that's changing height, I think of energy and I'm like, does energy work here? Does energy work in this situation? At first, it's not moving, so it has zero kinetic energy. Down here, it is moving, so it does have kinetic energy. Up here, it sort of has like a higher height to it. Down here, it kind of has like a lower height, right? It's fallen. And so energy does work in this situation. This is UG1 plus K1 equals UG2 plus K2. Now, we just said up here, it's got no kinetic energy. Down here, it's like at the lowest point, and so right away, we're just going to say that the height at that point is zero. And you might be wondering, and it's a great question to be wondering about, is how do you keep track of the height of a rod? Before we just had like a point, like a ball falls from here to there. Well, it's very easy to get a height, or it's very easy to think about height in that situation. Here's zero, and here's something above zero. But the rod has extension. And so, do you use the pivot point as your height? Well, in each picture as it's falling, well, the pivot point never changed, so the height stayed the same there. You might think the end, as this one actually does, it has a height here, and then it has a height here, and then it has a height here. But really what we're going to be using is the center of mass. Whoops. Center of mass as a way of keeping track of height. So actually, you know what? We don't even care about that middle one. So we're going to get rid of it. Just ignore that thing there. So here is the height. Higher. This is the lower height. This is H1. This is H2. And let's make H2, of course, is the lower one. Let's make that 0. Gosh, what is wrong with me? H2 is 0. This is H1. And if this is 0, then what is height 1? You can use the rod as a reference for distance, for height. And of course, it's half the length, right? And half the length is 0.75. So let's do this. This is mgh 1 equals k2. Now, you might be thinking mv squared over 2. Um, this is not translating, this is rotating. And so what we want is rotational kinetic energy, which instead of m, we're going to use rotational inertia. Instead of v, we're going to use omega. And don't forget the 2 on the bottom. So remember, it's analogous to mv squared over 2, but for rotation, I omega squared over 2. And so mass is 6, g is 10, and height 1, which is half the length of it, is 0.75. Look at this. So I, what is I? It's this, which is this, which is this. And so I is 4.5 times omega squared. And it's simply, solving for omega. 6 times 10 times 0.75 is 45. I do something wrong. I don't think I have done anything wrong. 45 times 2, and then divided by 4.5. But that's not over. We need to square root it, which is 4.47 radians per second is equal to omega. Sorry, I was running out of room. I still don't have enough room. For part C, how fast is the end of the rod moving when it is vertical? I want to know now, the end of the rod has velocity v, and that's a really easy equation to do, but I'm going to unfortunately destroy this picture that I've made to fit it in here. Part C, v is equal to r omega, which, yeah, we do want the end of the rod, so r is the length times omega, so let's see here, that is 1.5 times omega, 4.47. V is equal to 6.7 uh, meters per second. Okay. Yeah, you don't need parentheses here. Sorry, that's just my mind at the end of the day. Not really thinking. All right. Cool. That one is done. So this is a good example for the concept of energy. So this video will be on energy and rotational systems. Okay, cool. Forces and torque in multiple objects. Um, we have a solid sphere, mass m1, radius r. We don't need r1, just r. And we have mass 2 at the end of a string here. Once we release the system, mass 2 will accelerate down, and this solid sphere will begin to have an angular acceleration. And we have some values over here, m1r, m2, for these things. Cool. So let's figure this out. We want to know, what is the acceleration of the block and what is the tension in this rope. And one thing we'll start off by saying is that this acceleration of the block is related to the angular acceleration of the sphere. And just a real quick example, if this thing accelerates faster, right, and it's pulling on this rope, then this thing has to accelerate rotationally, faster. They're just related. Okay, we're going to start first by drawing a torque diagram of the sphere, and we'll draw a free body diagram of the mass down here. So here is our sphere, and it has a downward force on it from tension. It is angular accelerating that way. And let's draw a free body diagram for mass 2. I guess we can call this mass 1. Now it is accelerating downward, so I'm going to draw this arrow, which is m2g, a little bit longer than the tension force, which is Ft pulling up. Cool. And this is forces and torque. What we're going to do is write two equations to start off with. Our torque equation, sum of all torque, is equal to I alpha, which we're going to use this picture here, and then we'll write the sum of all forces equals m2a for this free body diagram that's right here. And we're going to try to use these equations together to figure out the acceleration at first and then Ft. So let's do this. The sum of torque, well, it's simply the radius of the sphere times the force Ft. Now the radius is, I'm going to say capital R times Ft equals the rotational inertia of a solid sphere, which is 2/5 mr squared. And before we get carried away here, there's two masses in this problem, m1r squared times alpha. My equations are too close together. And you know what? I think I'll leave it here for now. Let's write the sum of all forces equation for mass 2. Now it's accelerating down. We should put m2g here. Is that a capital M? Really bad about that. Let's fix that. And that's a capital M over here too, M1. Okay, M2G minus FT equals M2A. I would like to solve for A, but I don't know FT. Okay, I know mass 2, I know that one. I know all these things, but I don't know A, I don't know FT. And if I come over here, still don't know FT, but I also don't know alpha. If I could figure out FT, then I could just plug it in here and solve for acceleration, but I don't even have alpha. And so it seems like we're stuck. We technically have three unknowns because FT is repeated here. There's three unknowns, but we only have two equations. If we're going to solve this, we need a third equation. And the solution to this, you can pause and think about it if you want to. The solution to this is that relationship I mentioned at the beginning, that the acceleration of this mass here is related. There's a relationship with that angular acceleration. And of course, it's A is equal to R alpha. Interesting. Okay. So A is equal to R alpha. That's our third equation. Okay. Um, Now here's the deal. We want to figure out acceleration in FT. What I don't want to do, or what we shouldn't do, is start putting this in for A. Don't do that. Because we don't want to get rid of A. we want to keep a so that it's in the equation so we can solve for it. What we want to do is we want to rearrange this and have an equation for alpha. This would be a over r. Um, this is kind of the trick here. Let's do that again. So I want to substitute alpha instead. We didn't ask for alpha. So if we substitute this expression in here and get rid of alpha, that's okay because we never wanted to figure it out anyway. So what do I mean? So let's write this. Our ft equals 2 m1 r squared over 5. And we'll substitute in alpha as a over r. And by r, we mean capital R because the tangential acceleration, a, is um, this distance over here, which is r. So right away, r and r squared, we can get rid of one of those r's. Now, I'll go slow on this video. It's like, what's the point of doing a video if we just go faster, everything? We can cancel this r as well. And so now I have an expression for ft, which is 2 m1 over 5 times a. Yeah, I think it's 2/5 m1 r squared. Yeah, looks good to me. Can anything else cancel? Nope, I think that's it. So here's what we can do now. We can substitute this expression into this equation. We can say m to g minus 2m1a over 5 equals m2a. Oh, and of course we have numbers. I was like, how are we going to solve this? Of course we have numbers. Let's get all the a's on one side. So we'll say m2g equals 2/5 m1a plus m2a. Okay. Yeah, let's plug in some numbers here. So m2 is 10 times 10 is 100. But let's keep going. This is 2 times 4 times a over 5 plus 10a. This is 100 equals 8 over 5a plus 10a. Okay, what does this come out to? This is 1.6a plus 10a. So 100 equals 11.6a, which is a is 8.62 meters per second squared. Okay, so we figured out a, and label it as a, although these kind of go together. Let's figure out now what is ft. Ft is equal to 2/5 times m1 times a Okay, I just copied the same thing over. How silly of me. M1 is 4, and A is 8.62. So FT is equal to 13.8 newtons. Cool. We have acceleration, we know the tension. If we wanted to, we can figure out alpha if they ask for it. We can go back now, put in A, put in R, and figure out alpha. Cool. Let's do one last one. This is three objects. We have a three. So we have a block here with mass 3m. We have a block down here, mass 2m, held together by a string. And there is a pulley, which is a disk, mass m, radius r. So this is one without numbers. And first thing we want to do is figure out what is the acceleration of this system. Okay, so those masses will accelerate down. Let's draw first a free body diagram for both of these objects here, the 3m mass. Oh, I can do better than that, come on. 3m mass, which, okay, has a tension force on it. It has gravitational force mg, but this is numberless. This is 3 times the mass. This is 3mg, and it has on here a normal force. There's only one normal force in the problem, and so we can just label it as Fn. The other mass, mass 2, or I should say 2 times the mass, has gravitational force 2 times mg, and it has a tension force going up like this. Those are the free body diagrams for those objects. Let's draw a torque diagram, and that's an oval. Let's draw a torque diagram for the pulley. It's rotating around the center of axis here. Now, remember that strings cannot push. So the string here is not pushing that pulley. There is a tension force going in this direction here. And there is a tension force here. Oops. Very good. Now, let's talk about acceleration. We're not done here. We're not done with these yet. This thing is accelerating in this direction. This thing is accelerating down. And so which way is the angular acceleration of this pulley? Well, it must be in this direction. Angular acceleration. Always do, the fish is always looking down. Just do it like that. Um, and so if there is an angular acceleration in the clockwise direction, can these two tension forces be equal? One wants to go clockwise, one is putting a clockwise torque, the other one is putting a counterclockwise torque. And if it's going to accelerate, there must be a net torque. And so I'm going to call this F2 and I'm going to call this F1. F2 must be greater than F1. And if that's the case, down here, this is F2 and this is F1, to correspond with it. So let's write some equations and let's figure out acceleration. Now, we have three objects here. We can actually write three equations. Let's write the sum of all forces equals 3ma for this object. The sum of all forces is equal to 2ma for this object. And the sum of all torque, whoops, is equal to um, I times alpha. Okay, what forces go here and what torque goes there? So I'm just going to go one by one. The force that is causing the acceleration here is Ft1. That's it. Now, over here, acceleration, that's 2mg. I've made a oh, no, I haven't made a mistake, sorry. But yeah, it's 2mg. I was thinking of my labels M1 and M2, but we don't have that. It's just M minus Ft2 equals 2ma. And I should do these further apart. Cool. And then over here, okay, we have torque. Let's call this RFC2 minus RFC1 equals I. Oh, we need to put an I. But real quick, so I've kind of just done this without telling you about this, but let's make um, clockwise, the positive direction. So I'm making this torque RFT2 positive, and I'm making this torque a negative torque because it's counterclockwise. Because I know that it's going to be rotating this way, I'll make that way positive. Okay, so this is a disk. So the rotational inertia of a disk is, and the disk is mass m. So yeah, we're safe by just saying mr squared over 2 times alpha. So just a quick scan. We don't know ft1. We don't know acceleration. Okay, we know m, we know g. Oh, we don't know ft2. That's 3 unknowns so far. And then we keep going over here. Of course, these are unknown, but nothing really new. But alpha is, unknown. So we have here 4 quantities that are unknown. So we need 4 equations. We need more equations. And again, we're going to use the same trick we did last time, that A is equal to R alpha. Now, again, we don't want to substitute R alpha for A and get rid of A because we're trying to find A. What we want to do is make an expression for alpha, which is A over R. This is capital R. And so we will substitute it down here. So I'll start there. So R ft2 minus R ft1 equals mr squared over 2 times A over R. Now, how do I want to explain this? No, let's clean this up. So R and one of those R squares cancels. Now I'm just taking my time to explain all this. It's mr A over 2. We can still cancel another R. So this is ft2 minus ft1 equals m2 times A. M over 2 times A. Or ma over 2. Okay. I kind of just change it as I choose. It's the same thing. Let's make it nice and neat. Okay, cool. Now, if I want to get an expression with a bunch of acceleration, acceleration is here, but ultimately our goal is we've been used to this, so we want to substitute ft1. We want to substitute that over here, which we can do readily. We can take this and put it in there directly. Let's rearrange this for ft2. So it says ft2 equals, something. This is 2mg equals 2ma plus ft2. So this is 2mg minus 2ma equals ft2. And we're going to substitute that over here. So this is 2mg minus 2ma. We're substituting that for ft2 minus ft1, which is 3ma equals ma over 2. Now, this is 2mg minus 5ma equals ma over 2. Let's get all the a's to one side. This is 2mg equals, okay, 5ma plus ma over 2, that's 5.5 ma. But, let's make this, let's leave this in like a fraction form. So get a common denominator. This would be 10 over 2 ma plus ma over 2. This is 11 ma over 2 is 2mg. And what am I doing? This, you can cancel an m here. 2g equals 11a over 2. Let's multiply 2 times both sides, and let's divide by 11. 2g times 2 is 4g over 11. This is numberless, and so we have our a by itself here. 4g over 11 is a good answer. It's in constants, which is acceptable. Now, okay, we figure out a, and of course, what we're going to figure out here now is what is ft1 and what is ft2. Let's figure out ft1. So I'm going to use this expression, so it would help if I have it handy. I'm going to bring it over here, just so it's a little bit closer for us to see. I'm going to say ft1 is equal to 3 times m times 4g over 11. We're substituting. This is 12mg over 11. In terms of, known values, which is mr, fundamental constants, this is a great solution here. And we'll come back over here. Is this the best way to solve it? Yeah, 2mg minus 2m times 4g over 11. 2mg minus 2 times, actually, let's do this. 4 times 2 is 8. M times g over 11. And let's get a common denominator. That's 22 mg over 11 is minus 8 mg over 11 equals ft2. And 22 minus 8, what is that? 14? Get rid of this now. Now, this was part A, and this was part B, and this is part C. I mean, it's all together, right? But and hope you don't mind that I took time to do all those little steps here, just so you can see the algebra. If we wanted to, we could figure out the angular acceleration. Cool.